I will begin. Let me begin with a word of prayer. Once I'm up here. All right, I'll start. Heavenly Father, we thank you for this day. Again, I thank you for these students. Just ask you to be with us today. Help us to glorify you in what we do and just to cover the rest of the story of physics that we want to cover today. Lord, in my prayer, Lord Jesus, amen. So, yeah, turn in your homework, as is due. I will try to get that graded back to you Friday if all goes well.
Oh, wow.
We'll see what happens.
Good luck.
My device seems to be offline, huh? Come on. Okay. How about you don't be stupid? I'll get grief. I'm not connected to another network, you dummy. Here. Thank you. Here we go. Let's get nuts. So, what I was talking about last time, roughly speaking, was the history of physics. And we got to a point, I basically started telling you some things about quantum mechanics, right? There are plenty of things that I neglected in the 19th century. So, like, what other things happened in the 19th century? Some things that I neglected last time, thermodynamics. Statistical mechanics. There was tons of stuff that happened. I can't spell. StatMech. There we go. Lots that happened. I think Maxwell was involved in that, and Boltzmann, of course. And, things, you know, what am I doing? Ah! Well, will that do? Okay. Well, maybe it'll work. So I would say, you know, thermodynamics, statistical mechanics, there was a whole theory of matter that I think is largely forgotten. There are lots of undergraduates these days in math who are studying something called knot theory. Do you guys want to know what knot theory is? Theory of knots. So, I mean, it is literally that. Like, you know, what are the possible different ways to tie knots together? There was a theory popular around the time of like the, I don't know, 1860s or so that potentially could explain the structure of matter using knots. So people used to categorize all the different kinds of knots that were there because they thought that, excuse me, because they thought that it would explain possible forms of matter and things. So, of course, that has, you know, long since fallen into obscurity and no one cares anymore. But the fact remains that there's a stupid amount that is known about knots because, well, we used to think it was physical. All right, so that's one thing that I haven't talked about in the 19th century. But then 20th century, let's talk about that. So, as I mentioned, 1905, big time. You had special relativity. And more things. And then, as I was explaining last time, 1920s, basically quantum mechanics. All right. That's basically where we got to last time. Let me just read for you some other things that happened in the 20th century which I think are notable. Now, stupid teams. Let's see here. I had, believe it or not, I actually had the top hat all open and ready to go before class last time today. I was so ready. And then I forgot. Well, I mean, how would I know? If you disconnect the cable internet from this machine, it decides that it can't reconnect to the internet for some reason. All right, come on. You can do it. All right. Get this out of our way. All right. So, continuing, let me just read you some famous physical events of the 20th century. As I mentioned, Stern-Gerlach was actually 1923. That was when we discovered spin. In 1924, Bose and Einstein proposed statistics, the so-called Bose-Einstein statistics, that would be, in particular, we have two kinds of particles in the world. There are things called fermions, and there are things called bosons. So these have half integer spin. These guys have integer spin. So in terms of fermions, you have things like electrons, protons, neutrons. In terms of bosons, they're kind of unfamiliar. Probably the most famous boson that you know about is the photon. Photon is the quantum particle of light. All right. But there's something else more recent, something called the Higgs boson. It's even got boson in the name. So there's that. But the understanding that there should be two different kinds of particles with the two different kinds of spin, that's a relatively recent discovery. De Broglie came up with his wave model in 1924. As I mentioned, Heisenberg and Schrödinger, quantum mechanics in the mid-20s. Let's see here. In 1928, Paul Dirac proposed the antiparticle. So you guys have heard of antimatter, right? That was proposed in 1928. It was first discovered in 1932. First antimatter discovered. In 1932, also a fellow named James Chadwick discovered the neutron. In 1935, the Chandelier, I can't say that, limit for black hole collapse was found. So the theory of black holes from about 1935 or so, the start of it. Something called a muon was discovered in 1937. Superfluidity, 1938. Let's see here, what else should I tell you about? 1939, consider this, 1939 uranium fission discovered. That's actually really remarkable. So in 1939, theoretical physicists discovered the possibility for uranium fission. How long was it until we made a bomb? Like less than a decade, right? Do you know why Germany didn't have an atomic bomb? They tried. I mean, they were thinking about it. The leading German physicists who were formidable at the time, Oppenheimer among them, they did calculations, and we have it on tape. The Nazi scientists were at a British farmhouse after the war, so they have tapes of them talking to each other. And what happened was Oppenheimer made a miscalculation. He calculated it would have taken several metric tons of uranium, refined uranium, to reach critical mass for the bomb. And the thing is, it's really hard to create that kind of uranium. I think due to monumental efforts, like you've heard of the Manhattan Project, right? It took us thousands of people working for a long time to create, I don't know, maybe 20 kilograms of it, something like that, of which we made just a handful of bombs. We had to test one or two, and we used the two in Japan, of course. So Germany talked themselves out of it because of a miscalculation by one of their leading theoretical physicists. Is a blessing of God. It is nothing more than that. They wanted to. And it wasn't like some people say, oh, Oppenheimer did that on purpose because he was a pacifist. It's like, no, it was miscalculation. There's record of him talking to other scientists after the war, and he's like upset about having made the miscalculation, you know. So, as any good theoretical physicist would, right? But anyway, let's see here. In 1941, Feynman's path integral was discovered by Feynman. So, this quantum mechanics I mentioned, quantum mechanics is a kind of weird thing. It treats mass, things like electron, like it treats matter in terms of something called a wave function. It's a probability density cloud in some sense, right? So it treated matter in that way, but electricity, like the electromagnetic fields, it did not treat in that same fashion. It essentially still was thinking in some sense of the fields that propagated the classical forces as not being quantized. So before quantization, we say that physics is classical. So classical physics it's actually a technical term. It refers to things that are before quantum mechanics. Like even special relativity or general relativity would be counted among what we call classical physics. So Feynman's path integral in 1941 and the quantum electrodynamics that followed it. So this is the 1940 to 1950 QED. QED is not a pretentious thing to put at the end of a math proof. It's actually quantum electrodynamics. This is the theory which it's quantum mechanics. What it is it's quantum mechanics for photons. So it treats photons and electrons on the same footing, and their interaction is somehow described by these Feynman diagrams. Quantum electrodynamics is fantastically more technical than quantum mechanics. We still don't entirely understand. Well, okay, people will say that we entirely understand quantum electrodynamics. Some people will say that. What follows it, QFT, this is quantum field theory. And there are aspects of this that we probably understand at this point. But quantum field theory, there are infinitely many degrees of freedom. And the mathematics for it is not entirely understood. There are aspects of it which we still don't really understand the mathematics of. There are some physical principles that guide quantum field theory. There's something called a renormalization process. This renormalization process, you have these theories, they have infinities in them. What do we do in a math class when we find an infinity? We go, oh, we made a mistake, right? We start over, start again. What do physicists do when they find an infinity? What they do is they find an experiment to try to put the theory back on track, and then they absorb the infinity into some redefinable constants and they ignore them. This is called renormalization. It's an accepted practice in theoretical physics these days. And it has its, it has its critics, as you can imagine. I mean, if you want to see some pretty level-headed criticism of modern physical theory, modern physics theory, if you watch the YouTube videos, there's this lady. What's her name? Do you guys know what I'm talking about? You know what I'm talking about. She's got kind of curly hair. What's her name? I'll try to put a link in the description. But anyway, there are some pretty obvious flaws in the accepted methods for theoretical physics, which we're using to describe the physics which we accept as cutting edge today. There is still math to be done. Okay, anyway, getting back on track here. So, in the 1950s, this quantum electrodynamics was discovered, and the interesting thing about quantum electrodynamics is typically credited to Feynman, I can't say his first name, but Tamanga, Schwinger, and Freeman Dyson. Tamanga was a Japanese theoretical physicist in the 40s. This is one of my, I had a class called Rise of Modern Science. And it was suggested that the content of physical theory was a consequence of the societies in which it arose. And I said, this is crazy. Like, there is a physical reality. Physicists who are searching for truth will find that reality, as long as they let experiment guide them, right? Like, I fully believe that in time, astrophysics will be driven more and more and more to the Genesis account, because I think the Genesis account is true. And so, in as much as, stellar genesis and theories of stellar evolution and things seem to disagree with Genesis, I think it's a matter of the secular scientists being wrong. And I think that they do more experiments, as long as they're critical realists, they will be driven to the truth. I already think that we have an example of that with like Big Bang cosmology and, like I told you guys about before, inflationary cosmology, where we've been gone from it being a slow evolution from the initial singularity to where we are, to them being forced to say, no, at the start it was much faster. Like it's like the heavens were stretched out in an instant. Is essentially what inflationary cosmology forces them to say. Experiment forced that on them. And I think the same things will happen with other things like formation of planets, all these different sorts of things. But Tamanga was a Japanese physicist in World War II. So, I mean, it's obvious evidence. I mean, you can look across the, history of physics. It's obvious that physicists are finding something about reality. It's not a consequence of, what society or system of politics they were in, right? That's just silly. I think. Let's see here. Do you guys know when the laser was invented? What's that? 2004? Not that one. No, 1948. Invention of the maser and laser by Charles. Do you know what a maser is? It's like instead of light, matter amplification stimulated. I can't say it. Okay, going on here. 1956, the electron neutrino discovered. So there are other weirder things out there. There's something called a neutrino. Do you guys know what a neutrino is? I always misspell it. I got to be careful. So I can't spell neutrino. So the electron neutrino is this very, very ghostly particle in some sense. It just typically just zips through everything, doesn't really interact with it much. It takes giant vats of water and really careful detectors to notice these things. But there's a kabillion of them going through this room right now from the sun. Right? And there's different flavors. There's electron neutrinos. Later there's something called a tau neutrino. There's a neutrino corresponding to every lepton generation. Let's see here. I think those are the big things I want to tell you about in terms of the history. This sort of sets the stage for the PDF I have to show you. Let me erase some of this. Try to summarize what we got here. So physics, as it's currently understood, there are four forces, right? I put some quotes on that because that's probably not really the right thing to call them. There is gravitation, or just say gravity for short, all right? Now gravity, as we currently understand it, is probably best described by Einstein's general relativity. General relativity, as I said, 1916, okay? And then there is electromagnetism. This is actually from about, 1865 or so, Maxwell, all right? Now, of course, a host of other people were involved in the discovery of that over the ancient times, right? I mean, I think, there were people already playing with batteries and things back at the time of the revolution, right? It's not just then. It took hundreds of years to coalesce into the unified theory which Maxwell found in 1865 or so. There's also something called the weak force. Now the weak force you probably don't know much about. Anybody know what the weak force is? Yeah.
Is that like a chemical bond?
Chemical bond, that's relevant. It has to do with that. It's specifically most noticed in radioactivity. And most specifically, we see it in radioactive decay. That's what I think about when I think about the weak force, is radioactive decay. It's the force that's responsible, for example, for a neutron, right? If you have a neutron out in its lonesome, just sitting on a table somewhere, it has a lifetime, a half-life of about 11 minutes. So if you could somehow put 100 neutrons on a table and leave them alone for, 10 minutes, you come back, you only have 50 of them, right? Neutrons are not stable on their own. They're stable in atoms, where they're bound together, in the nuclei of atoms, where they're bound together with other things we call protons, right? So the weak force, it's the one that's responsible for radioactive decay. And then there's the other thing, which is the so-called strong force. What's that? It's, when you just look at it like this, they're really dumb names, aren't they? It's the weak force. It's the strong. Can you come up with better names? I don't know. But this is the one it binds nucleons together. So the strong force is what's responsible for protons and neutrons sticking together in the nucleus, right? That's one aspect of it. A deeper aspect of it, as I'll try to describe to you soon, is it's what actually keeps protons together. Because protons are formed by smaller things we know of as quarks. So I mean, of course, all of these things are speculative in some sense, right? Disclaimer, I don't think anything I'm telling you today is ultimate reality. I think ultimate reality is far more interesting than these simplistic descriptions of it we have in modern physics. I don't even believe in such a thing as a particle is real. I think that's a construct that we have to describe nature. I think whatever God is doing in terms of how he has arranged the cosmos, I think it's more interesting than that. We see sort of like shadows of that. I think that's what physics is. Of course, that's my philosophy, right? That's not physics. But so let me tell you a little bit about, so here, this right here, altogether, this comprises what we call the Standard Model. All right, so I'm going to explain to you a little bit of the history that led up to the Standard Model in this mini talk over here, all right? Go away. Not you guys. Stupid thing. Let me find my laser. Not you. This one. All right. Oh yeah, so I originally gave this talk in 2005. Still works though. It's based on a couple different things. Introduction to Elementary Particles by Griffiths, which is a wonderful book. Quantum Mechanics and Symmetries by Greiner and Mueller. I spent a whole summer working this thing out. That was a wonderful summer. Group Theory in Physics by Steinberg. It's okay. Representation of First Course Fulton and Harris is, yeah, okay, fine. These are less to do with it's mostly from Greiner, this talk, truthfully. Given in order increasing mathematical sophistication and decreasing physical interpretation. That is very true. All right, so I'll run through the initial stuff really quickly for you. Quantum mechanics, there's something called the Heisenberg operator, is it the Heisenberg operator? It's Hamiltonian, I'm an idiot. The Hamiltonian, and this is a wave function. If you operate the Hamiltonian on the wave function, it should give you I times the time derivative of the wave function. And that's quantum mechanics. That's the original quantum mechanics, like the 1920s kind. And you can study various things, like, for example, a symmetry of the Hamiltonian is something that commutes with the Hamiltonian. So what that means is that h times u is equal to u times h, all right? That means that you can simultaneously diagonalize the Hamiltonian and the operator. let's get past this. This is just mathematical stuff. All right, here we go. So back in the, I don't know, 40s to 60s, somewhere in there, we did experiments where we discovered these things called, we knew about, like I said, neutron was discovered, I told you earlier, 32? So if you do nuclear interactions with protons and neutrons, you start to notice that if you have one, you get the other, and like as you do interactions, there's some kind of interplay between protons and neutrons. And they have very similar mass, and when you have things with very similar mass, you think that maybe there's a symmetry that underlies them. That's a general idea. And so people started grouping. This isospin symmetry said that protons are kind of equivalent to neutrons, and so you can build these operators that rotate a neutron into a proton and a proton into a neutron, and you can do this math. You can define something called isospin. The proton has isospin 1/2, the neutron has isospin minus 1/2, great. They form something called an isodoublet. But there's more, There's also pions, pi plus, pi 0, pi minus. These are less familiar to our everyday experience. I mean, have you ever really experienced a proton or a neutron? But it's more familiar perhaps, right? You've heard people talk about protons and neutrons. Probably you haven't heard people talk about pions so much, right? I'm guessing. I haven't watched all the recent Marvel movies. Are they doing that now? I don't know. No. I mean, so there is no like, I heard there's something, well, let me not talk about the Marvel movies. Let's see here. So anyway, there's various interactions that go between, these are observed nuclear interactions between the pion, the proton, the neutron and the pion, the pi 0 and the proton, all these different particles. And if you study all these different interactions which are observed, you can look at the isospin and see that it's conserved. Like you go 3/2 before, 3/2 afterwards, 1/2 before, 1/2 afterwards, and so forth and so on. Like the isospin is conserved in these interactions. So that says maybe that all of these different particles are actually representations of some sort of thing, something called isospin symmetry. All right? That's like a very quick introduction to the idea. And that led people to look at invent something called hypercharge. Hypercharge has to do with isospin and regular charge. So this is like charge, as in the thing you're going to spend your whole next semester of physics learning about. Without me, you're welcome. And let's see here. I mean, I don't know. I'm pretty sure I'm not teaching physics. But anyway, so this is the hypercharge. This is the isospin thing. And you put them together, they give you the regular charge, like the charge of an electron is what, 1.609 times 10 to the minus 19th or whatever. That's probably wrong. Anyway, the neutron and the proton, they both have hypercharge 1. The pions have hypercharge 0. All right, so what? So all these particles are eigenstates of the charge operator, and the charge is their eigenvalue. All right, then what? Well, as the dust settled on the various particle accelerators that were going on then, and this was a special time. Like it was a time when there are people who were able to actually build accelerators in their garage or something because the technology hadn't got that out of hand yet. But as they organized things, and they had more experiments, there was more and more particles, so it became known as the particle zoo. There's the neutron and the proton that you have a vague familiarity with, but then there's these excited states of neutrons and protons, these sigma particles, and I don't know the name of that thing. The 3 lines particle, kaons, pions, the eta minus, the pi 0, the deltas, the gamma, sigmas. It's like a sorority in here, isn't it? But I probably shouldn't be presenting this at Liberty, Wait, do we have fraternities yet? No. Okay. Any of you signed up for the wine tasting class in the fall? I once got Professor Dromby to believe that. I'm very proud of that. She knows me better now. You just have to say it with enough authority. It sounds believable. But, no, as far as I know, no. Let's see here. So you group all these different particles according to their hypercharge and their isospin, right? And all of a sudden, you start seeing patterns in the hypercharge. Come on. In the. Are we doing this now? Really? You start seeing patterns in the hypercharge isospin plane, right? And so, like, these are. And then the question is, where are these patterns coming from, right? Right? So, one of the people who first understood these patterns was Gell-Mann. And Gell-Mann saw this pattern. Everything here was discovered. The deltas, the sigmas, the 3 lines. But there was this missing thing down here. So what did Gell-Mann say? He said, hey, there's a particle there. You're going to find it. And it's called the omega minus particle. He predicted it in 1961. And it was observed. It was found in 1964. So, you know, that goes to argue that there's something behind this isospin and hypercharge concept that nuclear physicists had. It seems like there's something, you know, if you can predict something that you haven't found yet, that's a pretty big feather in your cap as a physicist, right? That doesn't happen too often. It hasn't happened for quite some time in theoretical physics right now. We're currently, you know, decades without a significant event like that. Really, all of this activity, there was a flurry of activity from like 1920 to 1980 or so. And then after that, it really drops off. There's a few other big discoveries past 1980, but like it's just here and there. Top quark, most recently the Higgs boson. I'll talk more about that in a second. Okay, so next up, you can talk about something called SU3. And so if you want to, this would be a combination of linear algebra and abstract algebra. It's not a course we offer here. It's not a course many universities offer. But this is what you need to really understand the technical underpinnings of modern physics. Lie groups, the algebras, the representation thereof. And if you study that, you can start to see patterns emerging. All right? And I'll show you. So here. Well, more than that, before that. You can define something called quarks. Quarks are a fundamental representation of SU3 from this way of thinking. There's an up quark, a down quark, a strange quark, and then there are the anti-quarks, anti-down, anti-up, anti-strange. And the quarks have particular values for isospin and hypercharge like this. And then this is really weird. Their actual charge in terms of like electricity and magnetism kind of charge is fractional. 2/3, -1/3, -1/3. We have never observed fractional charge to this day. Charge is, every time we observe a charge, it is in an integer multiple of the electron charge. That is a fundamental observation of physics at this point. So these have not been directly observed. And yet, if you give them these fractional charges corresponding to these isospins and hypercharges, and well, they also have something called baryon number and strangeness, which is, I don't know. It's a bit, the terminology is a bit much to stomach sometimes. But you can use these, you can put them together using what's called a tensor product of a representation, which is just a fancy math word for saying multiply the representations. You multiply the representations, and when you do, you can take two quark, a quark and an anti-quark state, put them together, and when you do, this is how you do it graphically, and you get this pattern, which corresponds to the observed particle zoo. So, aha, if we have two quarks, a quark and an anti-quark, we can produce the kaons, the pions, and the pi 0 and the eta, just like we saw in nature, just like that. But more interesting still is, and by the way, so just to go back to the history a bit, so the patterns were observed in the early 60s. The omega minus was predicted in the mid 60s. But these are just patterns. It was just phenomenological. There's no basic theory to explain why these patterns were seen. And then in like 1967 or so, Gell-Mann, Sheldon Glasgow, and maybe one other, they proposed this quark model. They proposed that the neutrons, the protons, and the other basic matter could be built from quarks. All right, and I'm showing you how that's done actually, in terms of the representation theory. So this is also, if I take two quarks and put it together like this, I can get these kind of things. And then I take and add a third quark to those. And if I put 3 quarks together, graphically, I get this, which produces all of the known delta particles, the sigma particles, the 3-line particles, the omega minus, and then the neutron, the proton, and these other sigma particles and other 3-line particles. So using tensor products of 3 quarks, we're able to produce the whole particle zoo that we'd observed in the nuclear experiments of like 1940 to 1960, something like that. This must have been a very exciting thing to find if you were around in physics in the early 70s, right? So, and then in the early 1970s, so the SU3, excuse me. So the strong force is connected to this SU3 symmetry I'm talking about, all right? But the truth of the matter is, okay, so I have to tell you a little bit more. So SU3 is not just a theory of quarks. I mean, the strong force is not just a theory of quarks. That's part of it. But the strong force is actually described by something called QCD. QCD is quantum chromo. I can't spell chromo, but anyway, chromodynamics. So the strong force is sometimes also called the color force. The color force is it's mediated by something called gluons. You can't make this stuff up, right? Via interchange, well, let's say exchange of gluons. Gluons. If you get nuclear matter hot enough and dense enough, you can get something called a quark-gluon plasma, where the quarks and the gluons are like freed. You know what plasma is? Plasma is when the electrons are freed electronically from the like the nucleus, right? So you just got this sea of electrons and nucleuses, and they're just all kind of it's a big soup. It's another phase of matter. It's a plasma, right? This is, well, you've seen plasma, right? Fire is plasma, for example, right? So we've all seen plasma. Fire is actually another state of matter. The sun is mostly plasma, all right? But there are something like 17, 20 different phases of matter. So what is a phase of matter? A phase of matter is when, you're freed from, you have something that was bound before that's loosened, right? Like going from ice to water, you're going from the water particles being bound in the lattice of the ice to being loosed, and they're like loose in the water, right? That's a change of phase. Plasma, the electrons were bound to the atoms after they're unbound. Quark-gluon plasma, before you had the gluons, were bound, binding the quarks, and then there's an unbinding. So every time you have some kind of sort of unbinding, it's a change of phase. And there are something like 17 of these. But we usually say that there's 4 forms of matter, because those are the common ones, yep.
Are we confident in that number, or is that like what we discovered?
I wouldn't say I'm confident in that number. I would say that I've heard nuclear physicists say 17 or 22, but it was about 20 years ago that I heard it, so, Are we confident that there are exactly 22 or 17 phases of matter? I would say if you accept as a presupposition that the standard model as it exists works out mostly as we think it does, then yes, but, are we sure, 100% sure that the standard model is correct? I don't think so. But then again, you say, okay, well then propose something new, right? Well, we've been proposing something new for quite some time now. Let's see here. So, well, let me say more about that. Are we sure about, physics? Where is physics going? Where has it been? So, perhaps the first story of synthesis or reduction in physics is perhaps the story of Newton, where he discovered that his universal law of gravitation would simultaneously describe the motion of bodies on the Earth and the motion of bodies in the heavens, right? The idea that the same laws of physics bind the moon to the earth and the planets around the sun is a new idea. He's combining physics of the heavens to physics of the earth, right? That's a synthesis. This discovery of Maxwell, that electricity and magnetism were part of the same theory, that's another synthesis, right? So we're always trying to combine previously separate things in physics. That's the driving idea of reductionism in physics, right? It turns out this right here, electric and weak force, these were combined in like 1970 or so. That's approximate. There's something called the electroweak theory. So the electroweak theory says that before there was electricity and magnetism at higher energy levels, there's something called electroweak force. The electroweak force has a W plus, a W minus. Well, anyway, it has like force-carrying particles, all right? And the story goes like this. The electroweak symmetry is broken, and when it breaks, you get the weak force has its W plus minus and Z bosons. So this one is mediated by the W plus minus and Z bosons. All right, these are the weak force. And then, so you have the W plus minus Z bosons, and then you also have the photon, all right? So the photon, so the W plus minus and Z bosons, these are all massive particles. And the range of a force-carrying particle is inversely proportional to its mass. So the range of electrostatics, electromagnetism is infinite because the photon is massless. So it's a weird thing that happened in electroweak symmetry breaking, if you accept this story, which is that the weak force, the force-carrying particles for the weak force, they became massive. So the radioactive decay force is very short range, whereas photons have infinite range because they're massless. All right, so that's electroweak synthesis, and this has experimental signatures which have been found. So like people generally kind of more or less believe this. So then, of course, what do you want to do? Well, if you combine electricity and the weak force together, you'd also like to do what? Maybe the strong force is also part of this, right? So-called grand unification theories, or called GUTS. So there's been numerous grand unification theories proposed since the 70s, and none of them have borne out to be true as far as we know. I mean, they all tend to predict something called proton decay. In other words, that the proton is ultimately unstable. There are very, very strong tests of the stability of protons. Like protons are really, really stable. So if your theory predicts proton decay, you got some explaining to do. And that's a problem for pretty much all the grand unified theories. About this same time, though, we discovered something called string theory, right? So string theory is not a single theory. It's a theory of theories. Basically, string theory is just quantum mechanics for extended particles. So it turns out that that's really, really hard to do. Now, there's something called supersymmetry, which my thesis is roughly in, and the mathematics of that. But the supersymmetry makes the calculations way, way easier because supersymmetry links bosons and fermions. It puts them in some kind of pairing. It tends to make things cancel out. Do you guys know calculus 2? Let me explain it this way. In calculus 2, you have convergence and divergence, right? If you had a choice between a convergence-divergence problem with a particle with a series of positive terms, right? Problem 1, or problem 2, you have a problem of convergence or divergence with an alternating series. Which one do you pick? The alternating, right? Because alternating, all you need is it goes to 0 and it converges, right? So supersymmetry kind of makes all of the physics like an alternating series. It makes things cancel, which they wouldn't otherwise. It's super nice. But we haven't observed it. And supersymmetry comes with a heavy price. It predicts that there are double the number of particles we know. For the photon, there's a photino. For the electron, there's a selectron. For the proton, there's a sproton. There's a, I don't know if they call it that. Every particle gets a corresponding superpartner. And because of the way supersymmetry works, they can't be partners of things we already know. So listen, supersymmetry and string theory, that is where, those are, as my physics chairperson described when I was a young person. He said, I told him I was interested to go study string theory in grad school. He said, oh no, the siren song of string theory, it's claimed another. Like it bothered him then that all of the promising physics students in theory were going to study string theory. And it's still the case. it's incredibly productive mathematically. It's done new mathematics. Like we have discovered problems, we have solved problems in topology, which is the abstract shape of spaces that were here before understood with string theory, but it hasn't yet really produced physics. Yeah? No, the antiparticle is not the super, that's a different thing. That's just, oh goodness, that has to do with Dirac's quantum mechanics. That has more to do with Dirac's combination of like just quantum mechanics and special relativity. So it's something less esoteric. Like superparticles they're out there, man. They're out there. But I don't know. People who invented supersymmetry in the early 70s are still looking for it. So I mean, I'd love it if we found it, but I think the arguments against the state of current theoretical physics given by that lady on YouTube, I don't know the name of, Sabine Husfelder. Yeah, they're pretty good. they're kind of damning. So, in the biblical sense.